The preceding methods return scalar importances. Partial dependence plots return functional information, the shape of the response surface as a function of one or two hyperparameters. Where Fanover quantifies how much variance a hyperparameter explains, the PDP shows the marginal effect curve itself. Scalar scores underdetermine the questions practitioners actually pose. Is performance monotone in the learning rate, or is there an interior optimum? Is the optimum a sharp peak or a broad plateau one can safely occupy? Does the optimal value of one hyperparameter depend on another, an interaction for example? If a hyperparameter must be fixed for operational reasons, what is the performance loss across its range? These are questions about the shape of the landscape. The PDP answers them by visualizing the marginal effect of one or two hyperparameters on an expected performance, integrating out the remainder. So to get started, let's have a look at two different definitions. The ICE curve, individual conditional expectation, from Goldstein et al., fixes the complementary hyperparameters at the observed values of one configuration and sweeps the hyperparameter of interest over a grid tracing a single curve. The ensemble of ICE curves over all observations exposes heterogeneity in how different backgrounds respond. Second, the PDP, following Friedman, is the pointwise average of the ICE curves, equivalently the Monte Carlo estimate of the marginal effect obtained by integrating the cost over the empirical distribution of the complementary hyperparameters. So ICE gives the conditional responses. The PDP gives the marginalized one. Note, this is precisely the Fanover marginal function from the previous section evaluated under the empirical rather than the uniform measure. Concretely, the gray curves are the per configuration ICE curves, aligned at the left endpoint to compare shapes, and the red curve is their average, the PDP. The diagnostic content is the dispersion of the ICE bundle. Where the gray curves fan out, the response to this hyperparameter depends strongly on the background configuration, a signature of interaction that the average PDP conceals. This is why ICE and PDP should be read together, not the PDP alone. Transferring the construction from interpretable machine learning to hyperparameter optimization is a matter of correspondence. The trained model is replaced by the BO surrogate, the features of interest become the hyperparameters being explained, the background features become the remaining hyperparameters, and the training set becomes the hyperparameter optimization run history. What PDPs add over Fanover or Hypersharp is the functional form, monotone, peaked, interacting, rather than a scalar. But there is a critical caveat specific to hyperparameter optimization. Bayesian optimization does not sample the space uniformly. The acquisition function deliberately concentrates evaluations in promising regions, so the empirical distribution of the background hyperparameters is biased, and the PDP computed naively over the run history inherits that bias. This observation drives the remainder of the section. Let's have first of all a look at an example. So one-dimensional PDPs for all four hyperparameters we already considered in the previous sections, with the RUC indicating where configurations were actually evaluated. The shapes map directly onto the motivating questions. Max depth exhibits saturation, so a monotone improvement to a plateau. The learning rate shows interior optimum followed by sharp degradation. Subsample is essentially flat. For this to notify or to note, please have a look at the scale of the y-axis, indicating that this hyperparameter can be fixed with little loss. This is directly actionable qualitative information not available from importance scores alone. Selecting two hyperparameters yields a two-dimensional PDP, a marginal response surface over here, learning rate and max depth. The key feature is that the high performance ridge in yellow shifts with max depth. The optimal learning rate is depth dependent. That is an interaction rendered explicitly as a surface, something a scalar interaction index can flag but not characterize, and it answers the earlier question of whether one hyperparameter's optimum depend on another. Now we take the bias seriously. The root cause is that the acquisition function concentrates evaluations in high performance regions leaving most of the space sparsely sampled. This has two distinct consequences for PDPs. First, sampling bias in the marginalization. The background points cluster near the optimum, so the PDP integrates against a skewed empirical measure rather than the uniform reference the estimate implicitly assumes. Second, surrogate bias. The GP has high posterior variance in underexplored regions, and averaging those high variance predictions with well-determined ones distorts the curve. The upshot is that a naive PDP over a BO run can be materially misleading, especially for hyperparameters the optimizer fixed early. Two remedies follow: uncertainty-aware PDPs, which diagnose the problem post-hoc, and BO plus a technique called BAX, so Bayesian algorithm execution, which reshapes the data collection. The first remedy propagates the surrogate's posterior uncertainty into the estimate. A GP provides a posterior mean and a standard deviation at every query. The mean PDP is the average of the posterior means over the background. The PDP standard deviation is the root mean square of the pointwise posterior standard deviations. Around the mean, we place a credible band at the desired quantile. The band is directly interpretable as a reliability indicator. Where it is narrow, the surrogate is confident and the PDP is trustworthy. Where it is wide, the region is underexplored and the estimate should be discounted. This converts a potentially misleading point estimate into an honest uncertainty annotated one. Uncertainty bands only diagnose a fixed design. BOBAX, so Bayesian optimization, and Bayesian algorithm execution by Moosbauer et al. Intervenes on the data acquisition itself. It interleaves two objectives within the run. Optimization steps use the standard acquisition, sampling where performance is promising. Explanation steps use Bayesian algorithm execution. They select a configuration whose evaluation maximally reduces uncertainty about the target explanation, the PDP, rather than about the optimum. Concretely, BAX chooses the query with the highest expected information gain about the output of the explanation algorithm applied to the black box, so the surrogate model. The effect is a run that jointly optimizes performances and the fidelity of the explanation, so the resulting PDP is reliable without compromising optimization quality too much. Let's have a look at another example. So the comparison here shown is controlled for budget. Both runs use the same 48 evaluations. BOBAX simply reallocates a fraction of them from optimization to explanation. The dashed curve is the ground truth PDP, blue is the estimate from